Hi everyone, my name is Yuejiang. I'm a postdoc working with Professor Chelsea Pin. It's really a great pleasure to come here and present some of recent research on robot learning without action chunking. As you may have seen, there has been tremendous progress over the past few years in robot learning from human demonstrations. For instance, 2 years ago, we began to see this very impressive work on learning these fine-grained manipulations from Aloha or diffusion policy. And this approach has been further scaled at industry. For instance, at Pi0, they have shown this really impressive demo in solving laundry tasks. And more recently, this approach has been further scaled by other industrial players such as Gemini applied this idea to humanoid. So if you look at the recent progress in foundation model, many of these models have been following the same recipe. That is, we first collect a large scale of demonstration data, and then use this data to train these very expressive neural nets that may consist of a pre-trained vision language backbone, and then attach another additional action head. And this action head is often trained in a generative manner, for instance, through diffusion or flow matching, etc. So, in fact, this whole recipe has been already used in some other domains, for instance, language models and vision language models. We may wonder, are there anything unique in robot learning? In today's talk, I want to draw your attention to one element that is still quite different and I personally find very intriguing, that is action chunking. So what is action chunking? So the core idea is to group multiple actions into a single decision. So in the space of language model, oftentimes the model take a long sequence of past observations or context lens and then predict one token at a time. In contrast, many of the recent robot policies are built with very short context lens, but then predict a long sequence of actions simultaneously. After this chunk of prediction has been made, we're going to execute either the entire chunk of action or a big part of them. This idea has been used in a wide variety of recent policies. But it turns out that they have already reported some sort of different and even conflicting observations. For instance, in earlier work like ACT and diffusion policy, the author argues that it's very critical. This action chunk is very critical for achieving strong policy performance. For instance, the chunk need to be longer than 1 second or even longer. In contrast, there are also other papers showing that it's not always beneficial. There might be situations this is going to be detrimental. So what's really happening here? In today's talk, I want to first discuss some key strengths and potential limitations of this design choice. And after that, I'm going to talk about two methods we have recently developed to mitigate its limitations. Now let's first look at why action chunking. To understand this, let's first look at the property of the data we try to model. So compared with the earlier work in imitation learning, which often based on this script policy, recent work have been focused on this like a human demonstration. One interesting property of human behavior is that we humans do not make decisions just based on external state. We also have our internal state. For instance, our personal styles or preference. Do we want to go left or right, fast or slow? In addition to that, we may also have some sort of latent local strategies. For instance, what are the next post we want to arrive? Do we want to proceed or think a little bit, being idle for a while? These kind of internal latent states, of course, are not annotated in the data, but they can influence multiple actions in a row, introducing very strong temporal dependencies. And moreover, those kind of internal states could vary from one person to another, from one demonstration to another demonstration. Because of that, when we try to learn policy from human demonstrations, it's very crucial to capture this joint probability of actions across multiple time steps. And naturally, there are two choices. Either we expand this context length, or we can also try to expand this prediction horizon and execute all of them in a row. For now, let's first assume that our context length is limited. So what would really happen when we expand this action horizon? To understand this now, let's think about two choices. One is a very short chunk size or very short action horizon. This pi h, another with much longer chunk size, h plus d. without loss of generality, if we look at the last state or last step before replanning, what happens here is that for the long context, for the long horizon policy, what happens here is that the policy essentially can make decisions based on the information across many more time steps. It can directly observe this old state, and it also has access to the actions in many of these recent time steps. Because of that, it is essentially working or operating as long context policy. But of course, this comes with a clear drawback. It's going to reduce the frequency the policy can observe the environment or observe the state. So whenever there's something unexpected happening within the chunk, the policy will not be able to react. So basically, there's going to be an inherent trade-off behind this action chunking. It can greatly benefit the policy in terms of modeling the temporal dependency in our demonstration, but it's going to hurt reactivity. This might be particularly crucial in this stochastic, dynamic, uncertain environments. So oftentimes, when we deploy this policy, this is what we're going to see. When we run this policy with long chunk size, we're going to see this smooth behavior across multiple steps, but whenever the object starts moving, it's not going to be reactive, which we're going to see later. On the other side, if we reduce this chunk size, it's going to throw away all of these benefits of action chunking. The policy is going to be reactive, but may oscillate from one strategy to another. So how can we address this trade-off? And to answer this question, we're going to first talk about a test algorithm we developed recently. The core idea or the core motivation is that we just essentially want to combine the benefits of both work, long chunk policy and short chunk policy, at test time through a decoding algorithm, which we call bidirectional decoding. The core idea is actually quite straightforward. It's essentially a combination of action chunking plus guided resampling. What do I mean by this? Imagine at time step T, we have already made a decision about the next chunk of actions. Now, instead of executing all of them in a row, we can just execute the first time step or a small part of the chunk and put the remaining part into the memory of the robot. And then as the next time step T+1, here we can draw a large batch of candidates, chunk predictions, and then explicitly search for the optimal one with respect to the two properties we care about, basically the consistency with the prior as well as the reactivity with the current state. So for consistency, we can simply measure the distance between each of these candidate prediction and the prior decision. We can measure their distance either in the data space or in the latent space. And remove the candidate sample that is clearly far off the prior prediction or prior decision. But one thing to note here is that this sample selection criteria alone is not sufficient. The reason is that this is going to degenerate to this long chunk operation. For instance, if we think about this moving object scenario, when the object is moving, the prior decision might have become suboptimal. Simply picking new predictions close to the prior would continue with this suboptimal decision. So how can we become more reactive and adaptive to the new observation? To address this, we introduce another sample selection criteria called forward contrast. The key idea is to pick the sample that is optimal with respect to the future plan. So here we essentially try to maximize the likelihood through contrastive sampling. The key idea is that here we draw two batches of samples, a positive set that produced by the best checkpoint we have at hand, and then another negative set that come from a suboptimal checkpoint, for instance, an earlier checkpoint. Once we have those two set of samples, we can explicitly select the candidates that is on average close to the positive set and farther away from the negative ones. By doing so, we can essentially avoid this suboptimal plan with respect to the future. Yeah, so at each time step, we can repeat this process, explicitly optimizing for both the long-term consistency and short-term reactivity through these two objectives. And how does that work? So here we first evaluate this idea in the closed-loop operation of diffusion policy. So here we compare bit bidirectional decoding with three common baselines. The first one is vanilla random sampling. The second is warm start, essentially start the initial noise of the diffusion process from the prior decision. And another popular baseline called temporal ensembling, also EMA, essentially averaging out the new prediction and the prior decision. What we see from this simulation benchmark is that existing methods could indeed help to some degree. For instance, this EMA could improve the performance of the closed loop operation on some of these tasks. For instance, can transport, Yuejiang, etc. But it's not always beneficial. For instance, it can hurt the performance in push T. The reason is also kind of intuitive. So when there are multiple distinct strategies, simply averaging two decisions from distinct strategies would not necessarily give us a plausible solution. So because of that, it could be detrimental. And in contrast, our method, BID, can provide this more robust and substantial gain across the board. So on average, this method can produce about 30%, more than 30% relative gains compared with the baseline. And in addition, this idea can also be combined with the existing method, for instance, EMA, to achieve even better performance. And another very interesting property of this method is that it can actually benefit greatly from additional compute at test time. So generally, the more sample we draw, the more likely we can come up with the near optimal solution. Okay, so yeah, how does it work in practice? So here's the video of this bidirectional decoding on two dynamic settings. So the top one is this push T, but we intentionally perturb the location of the T block slowly but continuously. And on the bottom, we perturb the location of the cup. By the way, both of these two setups are modified from the great work from Shuan's group. So what we see here is that when we operate the policy with the vanilla action chunking, this is what's going to happen. The policy is going to be, as we discussed earlier, very slow in terms of the response to the object location. For instance, here, it's not able to catch this slowly moving object. And now if we reduce the chunk size, if we operate the policy in a closed manner, the policy is going to become much more reactive. For instance, we can see here that the policy can actually catch the cup. However, in the states where there are multiple strategies, the policy or the robot start to oscillate between different strategies. And of course, this is not ideal. For instance, this is going to lead to complete failures in this simulated push-T task. So yeah, how does our method works? So this is a result from this bidirectional decoding. By explicitly optimizing this long-term consistent and short-term reactivity, we actually see this smooth and reactive behavior in both simulation and real world. Yeah, so far all of this may look good, but we may wonder, are there any limitations of this idea? Yeah, so one clear limitation of this sampling technique is that so far we have just talked about this academic simulation or academic setting where the number of demonstrations are still rather limited, for instance, like just hundreds of demonstrations from a few persons. But if we keep scaling our demonstration at the industrial scale, maybe to millions of demonstrations, there might be a much wider variety of latent strategies. So when the number of strategies are limited, we can imagine that by sampling maybe just 20 or 30 samples, we can already have a good chance to find two samples that are close to each other in terms of strategies. But as this latent, the number of latent strategy grows, this algorithm may become more and more inefficient. Yeah, so how can we address this? As we mentioned earlier, so there are two choices. So instead of expand this action horizon, we can also consider extending this contact length in the hope that the policy can directly infer this latent strategy from history. Yeah, that's what we want to achieve next. But of course, building this history conditioned or long contact policy is not trivial. There are two fundamental challenges. The first one is oftentimes when we expand this context length, we often observe this clear performance drop. The reason is that the more features we put into the input, the more likely the policy may figure out may use some spurious features that can feed the training data pretty well, but do not generalize. And another critical challenge here is that when we extend the context length, the training process also becomes increasingly slow. Basically, the more frames we put into the context, the more memory we need to train the policy. This could lead to really slow training process. In response to these two challenges, existing works often either directly truncate the history. This has been widely used in many of these recent foundation models, for instance, RTX, Pi0, etc. These policies often just take as input 2 or 3 past frames. And this is clearly not ideal, right? Because it throws away the history that could be critical in some of these scenarios. Another alternative is to compress this history into very few frames. For instance, we can intentionally pick a few key frames or convert the whole history as a video trace into one additional image. And they can work pretty well in some of the settings, but ultimately they are essentially hand-engineered representation of history that throw away some information in the first place, and those information might be critical for subsequent decisions. So a natural question here is that is there a way we can learn the representation of history directly from our demonstration data? And this is what we want to achieve. To achieve this goal, we might want to first look at what's really happening when we expand this context length. One common issue discussed in the existing literature is that the learner may use a different set of features compared with expert to fit the data. For instance, the learner may already rely on the past action to predict the next action. And this is known as the copycat or initial issue in long context image learning. But it turns out that this phenomenon or this challenge is no longer happening to the recent diffusion-based policy. Instead, this recent policy often struggle to capture this critical dependency between the past and future actions. Motivated by this observation, we introduce a very simple fix that is what we call it past token prediction. The idea is actually pretty simple. We can, given a series of history observations, now we train the policy to predict not only the future actions, but also the past actions. So by doing so, we can explicitly regularize the policy to preserve the critical information about the past action. And it turns out that this simple idea can go a pretty long way. For instance, here we consider 4 real-world tasks. Each of them require some sort of memory from the history. For instance, move 2 spoons of beans to the bowl or replace one object by another. On these tasks, if we do not provide history as input to the policy, the performance is often very poor. And if we simply adding history into the context, it's not really improving the performance. It could become even worse. In fact, across 3 out of these 4 tasks, the performance dropped down to 0. And now if we train the policy by using this simple auxiliary task past token prediction, the performance can be greatly improved. For instance, in this like a LOTA setup for tape replacement, the success rate can go as high as about 80%, whereas existing methods fail completely. So this is about the performance or effectiveness of this idea. We also mentioned about learning efficiency. That's another challenge to train this long context policy. It turns out that what really matters for capturing this long-range dependency is just about the action head. And this property is rather independent of the visual representation. Because of that, here we introduce a multi-stage training recipe. So we don't have to train the visual encoder on in the long context setting from scratch. Instead, we can first pre-train this visual encoder in this conventional short context setting. Once this is done, we can pre-process all of these visual representations and save them in the cache. And then we can further use this cached embedding rather than a raw image to train this downstream action head in the long context setting. It turns out that this idea can greatly improve the learning efficiency they can achieve similar performance compared with training from scratch, but using only 10% or even less computational time. Yeah, so here are some videos about the influence of this PTP in practice. So on the left-hand side are the videos from the policy without this auxiliary task. What happens here is that the policy often struggle with this low-level behavior and fail to grasp the object properly. In comparison, when we train this history condition policy with this auxiliary task, it can achieve a pretty strong performance in this challenging history critical scenario. For instance, on the bottom is the aloha setting where the two arms can replace, just take out one cap and replace it by another continuously. Cool. So to briefly summarize in this talk, I first discussed the inherent trade-off behind action chunking. Basically, it can benefit the long-term consistency, but hurts short-term reactivity. To address this trade-off, we talked about this test algorithm called bidirectional decoding. It could address its limitation without modifying the underlying policy. And furthermore, we have also introduced this training recipe, path token prediction, that allows the model to capture this critical temporal dependency directly from history observations. Yeah, so with that, I'd like to close my presentation. And here are the two papers covered in this talk, and here are my amazing collaborators behind this work. Thank you, and I'm happy to take any questions.
Yeah. One question. Thank you for the talk. So my question is about the Bay algorithm you mentioned. In your demonstration, I noticed that your method can act really reactive and in real time. So from my understanding, the different policy need to use the action trunk because the model inference time is quite long. But in your demonstration, it is quite real time. I want to know the details about that, how you achieve this kind of real time movement.
Yeah, I think that's really a good question. So indeed, I think right now, I think the benefits of action chunking essentially come from two aspects. One is this, the modeling property. The other is like an inference time. So indeed, actually, when we try to operate the policy in closed manner, it's gonna essentially hurt this like inference efficiency. So actually, for the real world video, so in simulation, this is fine, right? Because but in real world, actually, we have to preserve a minimum amount of chunk size. For instance, here, we not run this bit fully in closed loop. Instead, we run with the chunk size of 2. So this basically we have to pick the chunk size that is somehow similar to like the inference time, or not too much slower than the inference time. But overall, I think the core idea of this bidirectional decoding is to introduce this temporal dependency across decision making or across chunks, and this will be critical even if we run the policy in a semi-open loop manner. For instance, we need to make sure if the temporal dependency go very long, we need to make sure the new chunk need to be consistent with the prior chunk. Yeah. And we can reuse the remaining part of the chunk.
Yeah. I have maybe a naive question. Have people tried like using some kind of recurrent state to use as kind of the memory?
Yes, absolutely. I think one of the papers is called like PCRN. I think that's also you try to use this history observations. But as far as I understand, they could work in some earlier settings, but they struggle to scale. I suppose this might be because of some sort of architectural design or some of the properties that, yeah.
So in the past token prediction, is there like an empirical value of how many past tokens you want to predict compared to future tokens? Like, or is that task dependent? Oh
yeah, I think that's a really good point. I think in practice, we do want to make sure the level of action dependency captured by the learner will be similar to the dependency in the demonstrations. And this could be actually probed or measured in the policy rollouts. So what we find here, actually, we didn't have time to cover this, but in the paper, we actually show that right now, we can design or choose this hyperparameter such that the resulting degree of this action dependency in the learned policy is similar to the expert. So this is like one way we can tune this hyperparameter.
Just to confirm, I want to make sure I understand the bidirectional decoding more. So you don't need to train the policy any differently, but only at test time you have to do some like additional sampling and like, choosing the best one or something?
Yes, exactly. So it's like completely training for an algorithm.
But is that very expensive or difficult to you need like the old model and the new model? You need to like run like 3-4 passes and you compare them.
Personally, I don't think it's a super expensive process. The main reason is that all of this computation can be done in parallel, right? So basically, you just draw a bunch of samples in parallel, and when it comes to this sample comparison, this can be done in parallel as well. So I wouldn't say this is super expensive, but this is definitely not a typical process used in the field. But I do think that this is probably where the field is going towards. So basically, we have tried to scale up training data and model capacity, but what can we do at test time? And this is just one of the first work showing that if we use test time compute effectively, we can actually address some of this modeling challenge.
Roughly, what is the time it takes for like one new set of action shots? So like you look at the state and then you predict, like you use the 3 checkpoints to make a prediction.
Yeah.
And then you like compare them and choose the best one and deploy it. Like how does that hurts?
Oh yeah. So I think generally, I think it slowed down the inference about 2 times through this kind of bidirectional, this sampling algorithm or decoding algorithm. But as mentioned by another student earlier, so actually, I think another critical challenge right now is that how we can accelerate this inference process so that we can further scale up the test time scaling or test time algorithm. And this is actually an area we are still working actively, and hopefully we can share some exciting progress the next time.
Oh, I'm curious actually. So right now, sounds like you can already push the horizon latent handles to task level. And then what's your thoughts on how to fuse that with the subtask, sort of more semantic level task representation with this action level or control level long horizon handling? With maybe more like sequential tasks where there are multiple subtasks that you have to handle, and then how to chain them together.
Within this work, we haven't explored this kind of like multi-stage setting, but I do agree that this is a very interesting setup. So very likely, I guess the field gonna maybe go down the route of like a hierarchical like a policy where we have this high-level policy to handle this like a semantic understanding of the stage or sub-process, and then we have this low-level policy. I tend to believe that actually figuring out this high-level stage might be easier to solve because of the video data available on the internet, but how to figure out this low-level history conditioning, I think that's still a critical challenge.